Hello, everyone. Thank you for joining me on this session as we're going to be talking about the future of databases. And we're going to be specifically looking at how modern technical innovations have allowed us to handle massive amounts of operational and analytical data like never before. But before we get started, I think it's best to go ahead and introduce myself, as you're probably wondering who the heck I am. My name is Rob Hedgpeth, and I am on the developer relations team at MariaDB. And basically, that means that I try to do anything and everything I can to help make the developer experience and the developer journey of using MariaDB products and capabilities as easy as possible. So, more simply put, my job is to make your job easier if possible. If after this session, you have any questions or really any feedback of any kind, please feel free to go ahead and reach out to me on email. You can follow me on Twitter or on GitHub. All right, so let's go ahead and jump into this. Now, before we jump into the future of databases and really taking a look at what we can expect going forward, we really need to take a look backwards, right? And by backwards, I think maybe the 1990s, early 2000 time periods when databases at that time were really starting to hit a performance wall. And this was largely due to the success of a little piece of technology you may have heard of called the internet. That, combined with application development at that time, were really becoming popular. And the process of those two becoming popular meant that we had increased data volume, increased data velocity, and in turn had the negative effects on the database so that you were seeing things like decreased throughput, and increased latency. So it basically was allowing you to do less, and it took more time. Two things that just don't jive well whenever you're using a database for your solutions and applications. And so when we started running this problem, we handled it in probably the simplest way, which was our first workaround wasn't very complex. We just decided we'd take out our wallet and buy a bigger machine, right? We'd buy something with beefier horsepower, whether it's memory, whether it's storage. But ultimately, we were just kicking the can down the road as every time we would start to hit this performance wall, we would just have to upgrade the machine. And there was times where our workload really didn't justify having that large of a machine. And so we weren't being able to account for, some more of the elasticity or kind of dynamic elasticity, allowing us to both scale up, right, to handle scalability, but be able to scale down. And so as at this point, we decided that, fundamentally we needed to change something. And so we need to go back to the drawing board. Well, as I mentioned before, we had already tried to solve this through hardware, and I kind of mentioned the reasons why. And it turns out that even whenever we took a step back, scalability is not a very easy problem to solve. And our next approach, we decided to get a couple of developers, some DBAs, sprinkle in maybe some sysadmins, all into a room. And we said, if the database can't really solve this problem, let's go ahead and try to solve this in code. And so this whole idea of sharding started to become popular, where you would create partitions, right? You'd manually try to configure these partitions with something like a partition key and group the data in such a way and buy a couple of different machines and be able to segment your data. Well, as you can tell, even me describing it, that wasn't a very simple solution by any means, and it was certainly very brittle because you had taken what the database management system had typically done to handle things like performance and scalability, and you really pushed that into the application development world. And ultimately, not only was it really difficult to maintain, but that's not very cost effective. And so we decided to take an even bigger step back to say, okay, we need to just wipe the table clean and see what we can do in order to really solve this problem. And something really awesome that came out of this was the Nosql Revolution, using different types of data models, which I won't necessarily get into, but different types of approaches besides just the relational model that we had been using for years in order to be able to solve some of these performance and scalability and flexibility issues at the time. Well, it turns out that, that we had to build a lot of the querying language stuff came from scratch, and so it's fairly primitive. Data models, and I won't get into the whole idea of data modeling, but it's very different than schema design in relational databases, and it can be tricky at times. And some of the bigger problems were that it didn't support things like ACID transactions or this whole idea of data integrity. It just wasn't really a concern for NoSQL implementations at that time, but certainly is still a concern for applications and solutions that you want to build for the enterprise world specifically. But overall, the whole idea of this was really good, right? It let us step back, and it let us kind of get back to the creativity of being able to determine how are we going to solve problems like scalability, flexibility, things of that nature. And so we started to think, okay, well, maybe if the NoSQL models won't work, maybe there is a better way, a different way. Enter this idea of distributed SQL. So you're likely familiar with those words apart, right? Distributed, I got a pretty good idea what that means. SQL, we've kind of gone into some of the relational aspects, and of course SQL is tied pretty closely to that. But what does it mean to have distributed SQL altogether? Well, put the most simply, a distributed SQL solution is a single logical database made up of multiple database instances. So in this diagram, you can see multiple database instances is the same as database nodes. They're interchangeable here. So these database nodes all work together. And the general idea is that these groups of nodes, or this cluster of nodes, is that you can simply add one or remove one in order to be able to maintain or get that elasticity, ultimately that scalability you're looking for. And then the data itself, as you can tell from the color coding, is distributed in such a way that you have, primary source of your information, or primary spot, maybe in database one, node one, where you've got this orange block. And then the two other blocks, you've got the orange block as well to signify that there's replicated data in the other instances. And it's in turn distributed across this cluster. So in this way, you can essentially be able to have a shared nothing architecture. So what I mean by that is that if I want to, as you can kind of see by this double-sided arrow, be able to communicate with the distributed SQL database, I can read and write by accessing any of the nodes. Underneath, the system is going to handle where particular data. So if you're writing something that maybe contains the replica, underneath the node is going to know how to communicate with the other node that maybe contain the primary source of information. And all that's going to be done through some parallel processing in an asynchronous way. And it's going to allow you then to have a very flexible manner of being able to communicate with the distributed SQL solution and the nodes while still being able to very quickly access your information. But the takeaway here, right, the largest takeaway is the distributed SQL solution is a relational database, right? And it's used the innovations of the past, right? As we looked at things like sharding and we looked at the Nosql Revolution, it's taken bits and pieces that we learned during those times, and it's solved the ultimate problem, which is scalability. And it's done so by still being able to take advantage of some of the modern benefits of things like dynamic elasticity, self-management, or what we can think of here as automatic rebalancing. So being able to rebalance our data, distribute it equally, or in a way that we can most efficiently use that throughout the distributed SQL solution. Maintaining continuous or very high levels of availability, of course, is very important within a database system. And then ultimately being able to use SQL, the structured query language, and all things ACID compliance and transactions, all the things that make it where you can create an enterprise grade application or solution on top of the database in a way that can scale in the way that you need it to. Okay, so that's a very high level view of distributed SQL. But a lot of times that's not enough to really gain, more of a practical knowledge or, more of a detailed view of what it's actually like to use a distributed SQL database. And for that, I want to look at an actual implementation. We're going to be looking at MariaDB Xpand, which is MariaDB's distributed SQL solution. Now, for those of you out there that may already be familiar with MariaDB, maybe you've even used it, the setup here on the left-hand side, right, on the left-hand side here, is going to look pretty familiar because that's a very standard kind of run-of-the-mill primary replica database setup. And it's something that you're likely going to think about whenever you think about MariaDB or relational databases really in general. And in this setup, you have entire copies of data that can be used for different things. Like if you want to read and write, maybe you access the primary instance. If you just want to be able to read and run a select of some sort, you may just want to access the replicas, one of the replicas that are in here on the left-hand side. And in these scenarios, the database instances allow the applications to connect to them directly, right, as a logical database. Now, on the right-hand side is a high level of MariaDB's new distributed SQL solution, Xpand. And just as I mentioned before, the last few slides on distributed SQL should look pretty familiar to the way that this is set up, right? Where all of the nodes inside of this database effectively all are able to communicate with each other in a single logical fashion. And of course, in a distributed fashion. So all the data itself is actually distributed among these nodes. Well, what does that really mean? Okay, well, for that, we want to dive just a little bit deeper into the architecture of MariaDB Expand. Now, from a deployment perspective, solutions and applications are able to communicate with MariaDB Expand through a single entry point. And in this diagram, the way I've kind of positioned that is by using something called MaxScale, which is MariaDB's database proxy. But ultimately, you could use any database proxy that allows you to have a single entry point and then be able to communicate with the underlying Xpand solution. And we'll get into a little bit more of why that is. But the main point here is that from an application perspective or a solution perspective, whatever that is, you have a single point of entry. Now, of course, all that aside, you could certainly have multiple proxies depending how large your solution, but to keep things simple, you have a single entry point here. And that's going to allow you to use things like an IP address and a port number, just like you'd be accessing any other standard run-of-the-mill database instance in order to be able to communicate with MariaDB Expand and ultimately take advantage of the distributed SQL mechanisms underneath. Now, once the application or the solution communicates what it wants to MaxScale or the database proxy, MaxScale database proxy are going to handle all the downstream communication. So what that means is that it's going to take the operation or the query and it's going to load balance that between reads and writes across the nodes and Xpand. And it's going to decide from a strategic perspective what the best way to be able to do that. And it's going to communicate with the MariaDB cluster or the MariaDB nodes themselves, that collection of nodes. And then because this is a distributed SQL database, all the nodes within the cluster themselves are able to talk to each other, which is where the communication underneath is going to come into play. Now, diving a little bit deeper into the inner workings of Xpand, so kind of below that level of the proxy, we can get a little bit more insights into some of the modern problems that it really aims to solve, namely, and first and foremost, really hearkening back to the beginning of this session, the idea of scalability or the problem of scalability. Now, using a shared nothing architecture, MariaDB Expand is able to combine both the compute and the storage of many of these independent nodes. So if you see node 1, for instance, in order to be able to eliminate bottlenecks and potential data hotspots. So you can think of a data hotspot as something that, it's just like it sounds, right? It's a hot place for either data to be stored or that you're somehow trying to pull out of it. If for whatever reason, the data that is organized in that node is being hit a lot more often. And so distributed SQL underneath the hood is able to perform some operations, which we'll get into here in a second, to allow you to be able to alleviate things like bottlenecks and data hotspots. Now, of course, just as I mentioned within the overview of distributed SQL, it's really important that we get an understanding of how nodes exist within a cluster, but also how the data is distributed within those nodes is also very important as well. And so when a new node is added, right, this is going to perform, as we saw in previous slides for distributed SQL, it's going to allow you to slice up the data in such a way, right? It's going to allow you to have a primary entry point and you've got some replicated information in at least 2 nodes. And as you add more nodes to accommodate different workloads and you remove them, right, to get that dynamic elasticity, what's happening here underneath is a dynamic data rebalancing. Now, from an elasticity standpoint, this means that the system can handle things like automatic failover, right? So if a node gets removed or just happens to drop out of the cluster, or like we're saying here, where you may have things like hotspots where information is much more accessed in one node, or it's getting put more in one node for whatever reason, the rebalancing system is going to keep all of that in check underneath the hood so that you as a developer that are accessing it within your application don't have to worry about that. Okay, so Xpand is what we call a symmetric architecture, right? So that means that essentially you can talk or communicate with any of the nodes in the database, which I mentioned before, similar to how we talked about it earlier in the distributed SQL overview slide. And this means that if you, for instance, execute a command like we've got a couple of selects here on expand node 1, expand node 1 can communicate with all of the other nodes, and it knows that it has the ability to go and be able to do selections, right? So this is the case if you didn't have a replica, or maybe you didn't hit the primary on this particular node, it could go and find the information in a different node, right? Underneath the hood, it's going to go and be able to execute that. And generally speaking, that really allows you to be able to do both reads and writes to any node within the cluster itself. Now, underneath the hood, all of this is really facilitated through a variety of techniques, right? Technical techniques like two-phase locking, which basically will make it where writes will block other writes, but they won't block reads. There's something called three-phase commits, which uses something called the Paxos protocol family, something that's very integral, which we won't get into, but is integral for distributed SQL solutions. And then something called multi-version concurrency control, which is going to allow you to execute things or everything really in parallel and provide a non-blocking way to access the data within the distributed SQL solution. And ultimately, all of this comes together to create an extremely efficient approach to ensuring the data integrity that you'd expect within your standard relational databases, but also being able to maintain an extremely high level of performance that most modern solutions and applications expect these days, right? And I think we know that. Now, as I mentioned before, a key factor of distributed SQL and its ability really to maintain high availability is a must-have, not necessarily just within distributed SQL, but within any database. And this is really facilitated through the idea of replication or copy data that you can use in another instance or another node if something happens to go down. Now, moving beyond just the scope of having your cluster in one single area, it's likely going to be the case that you may have nodes spread across different zones, right? Different locations, or even have clusters separated between these different locations. And this provides you the ultimate amount of resiliency in the case of, being able to maintain high availability, but also in, heaven forbid, some kind of disaster happens that you have the ability to recover. And so if a node in a particular zone fails, then the data will remain available through replicas in other zones. So a different zone that may have the data already replicated. And this is going to be, facilitated through some kind of parallel streaming that happens underneath the hood that, again, you don't have to worry about as a developer. You're just accessing the data, and these things are handled underneath the hood. Now that you've gotten a gist of distributed SQL and ultimately an implementation of it with MariaDB, you're likely wondering, okay, well, what's the performance like? Like with anything that you want to be able to control data or manipulate data, you're going to want to know, well, what kind of performance benchmarks can I expect? Now, for that, I've got a few benchmarks that we've been doing lately, and of course, we've got many more lined up that we're working on actively now. But first, it's important to point out that if you look at this graph, it is based on throughput and latency, right? And sometimes you may see benchmarks that only focus on throughput, but for distributed SQL specifically, it's important to focus on both, because not only do you want to know throughput or the amount of queries per second, but you also want to know how much time that's taking, right? The latency itself in order to be able to execute these or have these completed. And so taking a look at this chart, you can see that we have spun up 64 nodes, which is actually pretty modest for a distributed SQL solution. But even within this example, you can see that it scales extremely well, being able to produce or perform hundreds of thousands. Of course, we put in here 860,000 writes per second in under 10 milliseconds. So that's pretty fast, no matter really how you look at it. Now, we also went ahead and took a look at reads, and you can see that we even have even a higher number of reads, which is to be expected, of being able to access 10 million reads per second with 128 nodes. And this is all done under 5 milliseconds. So pretty good performance numbers. But one of the things that I've focused on almost exclusively throughout this session so far is we've been looking a lot at OLTP, or online transactional processed informations, and those kind of workloads, which makes sense because a distributed SQL solution ultimately is an OLTP solution, right? Something your operational solution and application can use in order to be able to scale massive amounts of data. But something that we're excited about at MariaDB is some new functionality that allows you to perform extremely performant, or create extremely, quick, dynamic, performant queries, analytical queries, and aggregations based on the amount of data that's in distributed SQL. Now, again, this is all OLTP, or operational data, but we're allowing ourselves to be able to perform analytical queries at a very performant rate. And so we're going to jump into that a little bit. Now, this whole idea is really facilitated by the idea of something called a columnar index, which you can use to perform extremely fast aggregations on massive amounts of data. So that can't be understated, right? And when we talk about aggregations, right, it's pretty straightforward, and this is a pretty simple one where we're performing an average. Now, typically, whenever you perform a query like this, what's happening is that you're going to have an entire table scan, right? So you got these large tables that contain a lot of information, and you want to have it, and it's going to have to take a look at the entire table. Now, there are other approaches like columnar storage that allow you to kind of get around some of these things, but we're still using this in typical row-based storage, but we're allowing ourselves to use something called a columnar index, which then allows you to be able to use the data like it's in an analytical or OLAP storage mechanism, right? So something like data warehousing, or some of your more real-time analytics type solutions. And of course, these columnar indexes can actually be used in combination with your traditional row-based secondary indexes. Okay, so what does this look like? Okay, so if we create a table, we can create a single columnar index. And as you can see here at the bottom, that's going to allow us to be able to index, in this case, when we use the keywords columnar index, to index the invoice total. And this is going to allow us, when we use the invoice total field inside of a query, to run an analytical query extremely quickly. Now, you can also go ahead and drop the index just as simply by using drop index, but you also have the ability to create composite indexes, or multi-column indexes. And this will allow you, in combination with the secondary indexes that you can create from a row-based perspective, in combination with these columnar indexes, be able to take advantage of both OLTP and OLAP-based data or queries that you can execute all in one solution. Now, just like we looked at before, you're likely wondering from a performance standpoint, what does this really mean? Now, we've done some preliminary testing internally, and what we're seeing through our preliminary results is that we've seen a gain or performance boost based on typical OLAP indexes, OLTP indexes and OLTP data, versus what we can accomplish using a columnar index. So in this situation, we're actually looking at no index at all. We can see that we have, on 1 billion records, more than a 10x improvement by adding a single columnar index. So we're seeing a lot of potential out of this, which is going to allow us to be able to use both OLTP and OLAP-based querying within our applications within a distributed SQL solution. I'm very excited about this. And with that, I would like to say thank you very much for attending this session on the future of databases and distributed SQL. If you would like to see more information on how you can work with distributed SQL and even take a look for yourself at an actual implementation, please feel free to check out the content on MariaDB.com. There you can get access to a free 45-day trial, which can allow you to use unlimited nodes and cores. You can check out the official documentation and product information on the website as well. But like most things these days, the simplest way to really check something out is in the cloud. So if you would like to get started with MariaDB SkySQL, you can do so completely for free using a $500 credit. And you can even check out Xpand, a distributed SQL solution, in just a matter of minutes. Again, completely for free. And with that, I'd like to say thank you very much for watching the session and happy coding.